This is ST-Gait, leveraging spatio-temporal convolutions for gait-based emotion recognition on videos. So first, let's talk about emotion recognition. So emotion is a really big part of human communication and social understanding. I think we all can relate to like having a talk with someone and looking at them and inferring what they're feeling based on maybe the way they're talking, the tone of their voice, or their facial expression, the way they're holding themselves. And we react accordingly. We try to inflict or change the way we're behaving so that we can affect someone. So if they're feeling bad, we can try to make them feel better. So a lot of this communication can come from verbal cues, which mean someone can tell you what they're feeling, but also from nonverbal cues like facial expression, body language, and gait, which is the way someone walks. And previous research has already suggested that the way someone walks or the gait contains social markers, and also Voxar in 2009 has already successfully used gait as a nonverbal cue for the emotion recognition tests. So we can leverage gait for this task. And why is it interesting to use gait? So when you try to infer to recognize emotion using things like facial expression, or using some other devices, you can actually change the way someone is behaving or expressing themselves. So you're interfering in the data that you're collecting. So by using gait, you can just put a camera somewhere, and the person, the user, is allowed to freely walk. So you're not interfering as much as you could otherwise. And you can use it in some applications like healthcare analysis. For example, because interment patients, they can struggle with mental health issues in interment, and by collecting this data, you could allow healthcare professionals to more quickly react to the way to the struggles of the patients. You can also use it in smart cities or, for example, urbanism applications where you have this parks, streets where people may be feeling insecure or angry, and you can actually interfere and do and change the way people are relating to the city. So there are some really interesting applications where you can use gait. So how do we do this? So gait is the way someone walks. So you can imagine it as a sequence of skeletons. So you have graphs, right? The data shape, there are graphs. So you have the skeleton of the person in the spatial area, and you have the temporal edges, meaning the temporal sequence of the skeleton through time. And you can use spatio-temporal graph convolutional networks to process this type of data. And we used STGCN++ as a backbone for our work because it has some mutable kernels for the temporal aspect of the convolutions, and it has some optimized processing of the spatial edges. So this is our proposed architecture, ST-Gait++. So we extract the skeleton inputs. Maybe we have a body pose extractor from video, a live feed or something like that. And we extract the skeletons and input it into the network. And then we get the inferred emotion. We trained this on the eGait dataset, which is a state-of-the-art dataset. And it has 4 emotions: happy, angry, neutral, and sad. So what did we achieve with this? So we got state-of-the-art performance. We got 87.5% accuracy. At the time we were writing this, the humane work wasn't out yet, so we were comparing to STEP, which was the state-of-the-art at the time, with the 83% accuracy. We also converged faster during training. And this is interesting because when you have lower computational resources, you actually need to train and do experiments, and this allows you to do them faster, try more things. So we were able to converge faster as well. So again, we improved the state of the art by almost 5% in accuracy. And in comparison with STEP, the state of the art, we also required 72% less apex for convergence. And we were able to also improve the performance on ambiguous scenarios. In psychology literature, there are some emotions that are harder to distinguish among themselves, and we were able to perform better in happy and neutral emotions than STEP. So just to bring some discussion to our reality in Latin America. So it's hard to find data, it's hard to find good quality data, and for specific tasks such as emotion recognition through gait. And there are very little data sets, and they're not suited to Latin American reality. So gait, for example, is very centered on Europe and North America. So because emotion expression is also linked to culture, it's possible to infer that this application wouldn't work well in our reality if we were to use it in Pacific, where I'm from, or some other place in Latin America. So I just wanted to bring this to attention, since we're having this crowd here from Latin America, that we as researchers could focus more on building good quality data sets that are focused on our area. So in conclusion, we used gait for emotion recognition. We obtained a better performance than state of the art by improving the architecture. And we also got important insights about the lack of data, the difficulty of data availability, especially for our scenarios. We want to bring applications closer to us, so this is the way we should go. So that's it. Thank you.
Thank you very much, Maria Luísa. We have time for a couple of questions. Have you tried to include, like, I don't know, some kind of metadata? Like, for example, I don't know, I can think of something that is really trendy today that include like descriptions of what the person is doing, like, oh, this person is walking very fast or something like that. Because you are just considering like the geometry of the person. I mean, it's just like a graph of the key points. So
yeah, there's actually something called effective features that are extracted as well, but we're not using some other metadata. Okay. Just these effective features.
Yeah, so I'll say I really appreciate the part. I mean, first of all, great talk, but also I really appreciate the part at the end talking about. I was going to ask about some cultural differences and things like that, and did this kind of work. But so if you have more thoughts on that, I would love to hear more thoughts. But I also have a concrete technical question as well about them. You said it's 72% fewer epochs, but I was wondering in terms of like computational time per epoch or sort of additional complexity or anything like that. Is there any kind of like is 72% fewer epochs? Is that an accurate reflection of the actual training time?
Yeah, during training time, it is actually very much faster in seconds. But during the runtime, during inference, it's actually longer. We have on the paper a table for that. You can look it up. So during inference, it does take longer, but during training, it's much faster.
okay. We'll have maybe one question more. If not, thank you so much, Maria Luísa.